Alright, welcome back. Now I told you at the very beginning of this long lecture that the first 4 parts would be all about in situ weather observations. Observations that are taken by instruments that are touching what they are measuring. And so we're just about done, we're just about ready to wind up those last of the in situ observations, and the one that I want to talk about is rain gauges right now. Now, obviously rain rate doesn't, or total rainfall or anything like that, doesn't directly affect the production of wind power, although I guess it would have consequences for solar power and so on. But it is part of the general climate of a region and the weather that's affecting the crews working there and so on. And there certainly are many different technologies for measuring the rain. I mean, even just thinking about something as simple as like a backyard rain gauge, there could be like a standard rain gauge, where it's literally just something like a test tube mounted onto a pole, and it is graduated. In other words, it has little markings along the way that tell you 1 inch, 2 inch, 3 inches, or by centimeters or whatever. That's just called a standard rain gauge. Standard rain gauges aren't very accurate or very precise, because certainly not very precise. You just can't tell small differences in the volume or the height of the column of water on a standard rain gauge. You'd be way better off if you're trying to get precise measurements by using a funnel catch rain gauge. This is one where there's that big wide opening at the top of the rain gauge that captures a large amount of rain and then deposits it into a cylinder, which is graduated, but the markings are much farther apart, for their scale. So, like I have a funnel catch rain gauge in my backyard, and 1 inch of rain makes a, column of water about maybe, I don't know, 6 or 7 inches tall on my rain gauge. So, a tenth of an inch of rain is maybe a couple, maybe as much as almost an inch of height. I can very easily tell, with great precision how much it rained each day. That's one type of technology. Another type of rain gauge is what are called a wedge rain gauge, sometimes called a farmer's wedge, where it's narrow at the bottom and wider at the top. And this is a particularly good type of rain gauge if you have a lot of small rainfall events. Because it's very narrow there at the bottom, even a small amount of rainfall will make relatively big differences in the height or the depth of the water in that wedge. And so you can definitely tell the difference between, 3/100ths of an inch of rain and 5/100ths of an inch of rain. Or the difference, there's very good precision at small rain gauge differences, whereas as you get higher and higher up the column, the width of the wedge gets bigger and bigger, and an inch of rain might only make an inch deeper area inside of that wedge, and so you have lower resolution for heavier rainfall events, because really what is the difference between getting 2.54 inches of rain and 2.56? Okay, the difference between these relatively large rainfall events doesn't really matter, where it's mostly going to run off anyway, whereas differences between very small rainfall events are important, especially to like farmers and so on. But there's all kinds of really cool rain gauges, and this is actually a video showing the inner workings of one of my favorites, a tipping bucket rain gauge. In a tipping bucket rain gauge, there's a little mechanism inside. There's a funnel that's collecting the rain and dripping it down into this little apparatus here that is tipping back and forth. It gets a amount of liquid water equivalent to like 1/10 of a millimeter or something of rain, and then it tips over, draining that water away and filling up a bucket on the other side of the little apparatus until it gets to the amount of water equivalent to like 1/10 of a millimeter of rain or something, and then it tips the other way. And as the rain falls, it tips, and it can record, if it's hooked up to like a data logger, it records the time every time it tipped. Well, then by the total number of tips that happen during a storm, the total amount of rain. For that matter, by how many times per minute it tipped, the rainfall rate and so on. This can give you very precise information. It's even during very small rainfall events, very big rainfall events. This is one of the standard ways that we measure rainfall, like at a National Weather Service office or so on. And there's other fancy schmancy high-tech ways to measure rain too. There's types of rain gauges that actually weigh the water rather than try to measure the depth. That can be more precise and so on. But we can, again, we're not going to sit here and try to take a look at lots and lots of different kinds of rain gauges. Now I want to talk about observations that we can take away from the surface and the boundary layer of the Earth. Setting aside weather stations and instrumented masts and so on, let's talk about getting measurements of the winds higher above the surface of the Earth. Well, there's one very low-tech way to do it, and that's called a pieball. Pieball is a word that is just sort of put together from 2 words, pilot balloon. And pilot balloons or pieballs are an extremely low-cost way to get measurements of the winds above the surface of the Earth. Now, why this word pieball? It comes actually from hot air ballooning. A couple times over the years, I took classes to field trips where they watched the launch of a hot air balloon. And when the balloon's just about ready to go, the very last thing the pilot of the balloon wants is a surprise about what the winds are doing 50 feet above the ground or something like that. So before he's ready to launch, he takes out just an ordinary helium balloon like a kid would get at the grocery store, and they call out, "Pieball!" and they let the balloon go. Now, in the context of like hot air ballooning, they just watch the balloon and they notice like how it moves. Okay? And they see, oh, looks like at about 50 feet up there's this, low-level jet stream or something, and we gotta be careful about that when we take off, or we gotta wait until that dissipates, or whatever. There's no equipment involved or anything, it was just a balloon. Well, actually, pieballs are the same sort of way. Now, some years back, I actually took some students out, and we, in one of my classes, actually launched some pieballs. And so here's an example of what a pieball looks like. They're filling it up here with hydrogen, I think is what we were using that day. And, they're about the size of like a big beach ball. But that's all it is. It's just a balloon. And we take the thing out there, and somebody went out to the end of a field, and they're holding it up. And at the same time, then the other students are like across the field with an instrument on a tripod there like that. Then that instrument is called a theodolite. Now, theodolite is a word that you probably don't use in your day-to-day life. A theodolite, pull up a Google definition here, it says that it is a surveying instrument with a rotating telescope for measuring horizontal and vertical angles. It's like a telescope, and you keep that balloon, that pieball, in the sights of the telescope, and it records both the angle, with respect to north. Again, you have to calibrate it so that you know exactly which way is north. And it also keeps track of the angle above the horizon that, in this case, the balloon is. That's called elevation. So the theodolite will keep the balloon in its sights and then track it as the balloon floats away. And then the theodolite is actually rigged up to a computer that's actually, or a data logger or something that's keeping track of this. Now, the pieball rises at a known constant rate, a certain number of meters per second. You actually measure that by measuring the, you hook it up to like a little, like a scale before you launch it, and you can figure out how hard it's pulling, how buoyant it is. So based on the known constant rate of ascent, the computer program or the data logger or whatever can do the math and all the trigonometry that says, okay, if after this many seconds I know the balloon is this high, if it's now at this azimuth angle and this elevation angle, this is its new three-dimensional coordinates. So that it's at this location. Well, now 2 seconds later, if it do the same math again and now it's at this location, I know what the winds must be. It just simply uses tracking the balloon to figure out how the balloon is moving and therefore how the winds are moving. This is pretty slick and pretty low tech, and it's a great teaching demonstration. And in fact, this is a big part of the way a lot of the world launches and get balloons and gets weather information. The students, were doing it. We could get the school to agree to do it because it was cheap. I mean, we, borrowed the theodolite from some other school. We got a tank of hydrogen and a couple of these balloons for a couple cents a piece, and it was an easy way to do it. And you just keep watching the balloon fly away until you can't keep track of it anymore. Either it goes too far, it goes over the horizon, or it just got too high and you can't see the balloon anymore, or it goes into clouds or whatever. And the computer program reports back information like this. Here it was dividing up. I just thought it would be interesting to review. Here it divided up as we floated away the balloon, the U and V components of the wind at different heights. So we were able to track the balloon as it went up and see its west to east component U and its north to south component. South to north component V as the balloon went up. It's just data. But see what happened there? We were able to track the balloon and actually get these measurements. They're ridiculously cheap. Man, every country in the world launches these things, even if they don't do anything else for meteorology, because they're just so cheap and easy to do. A lot of developing countries launch these near airports just as a way of knowing about like the wind shear and so on in the vicinity of the area where they're conducting flight operations and so on. It's just a balloon, and you can just generate hydrogen gas on site using a number of different technologies. But the problem, of course, is you have to actually be able to see the pieball for this to work. Once the pieball is too small, it's drifted too far away, or if it's dark outside, or if it drifts into the clouds, you're done. There's nothing else that can be done about this. Now, if you really want this to work, you can find ways to make it work. For example, if darkness is your problem, a lot of African nations launch pieballs, again, around airports and stuff like that, to make sure that they can do safe flight operations. And all they do is they attach a string to the balloon, and some number of meters below, they hang a candle. They literally just light a candle on that string down there, and then let it float away. And then even at night, they just keep that candle in the sights of the theodolite, and from that they can get their wind information. I choose not to think about the safety issues of having that candle near all that hydrogen, but it can be done. In fact, the Canadians do it too. Nowadays, they usually use like a glow stick instead. It's a small glow stick that they use. But I mean, if they're just trying to get very cheap weather information about the winds above the ground, a pieball is a great choice. But obviously, there's no instruments on here. The balloon is not, the pieball doesn't know anything about the temperatures, the pressures, the humidity, or anything like that. If you want to go big with that kind of information, you're going to have to go for a weather balloon. Now, weather balloons are a lot bigger than pieballs. When you saw those pieballs in those previous figures, oh, they were a little bigger than a beach ball, but they weren't that big. Weather balloons start off about as big as a man. I don't know if I have a better picture coming up with them. And as they rise, they're going to be carrying a package of information, a package of instruments called a radiosonde. That is the radiosonde you see hanging at the bottom of that string right there. We'll see a better example of one in a little bit. A radiosonde is a little package of instruments with a thermistor and a hygrostor and so on in it. Now the balloon itself is going to rise and it's going to expand as it stretches out, as it gets to air that is lower and lower pressure. As it rises, it'll just keep expanding, and within about an hour, it's going to be about the size of a school bus. These are very, very stretchy balloons, the material they're made of. And within about an hour or so, the weather balloon will pop and plummet back to the ground. And between the stretched out latex of the balloon and a little paper umbrella that's a parachute that's hanging from it, the whole apparatus will just sort of fall back to the ground and maybe get recovered, maybe not. The Weather Service doesn't go out looking for them, but they usually include on the radiosonde, there's like information about how to mail it back to the Weather Service for it to be reserviced and so on. But they only fly for about an hour or so. Don't get the idea that like we put weather balloons up there and they float, for days or something like that. No, within about an hour they fall back to the ground. And during that time, they'll get to typically about the height of the tropopause, maybe up into the stratosphere a little bit. Here's actually a picture of a modern radiosonde. Older radiosondes were about the size of a shoebox. Newer ones are a little bit smaller than that. Maybe because it's lunchtime, but the only thing I can think of that's an example of how big they are is they're about the size of a box a Big Mac comes in nowadays. Okay, so that's about their size if you're having trouble seeing the scale here. They weigh practically nothing. They have to be very light for that balloon to be able to lift them off the ground. So they certainly weigh less than a half a pound. They try to keep them under about 200 grams, which is I think 6 ounces. They are pretty darn light though. They just have a little temperature thermistor on there. They have a little hygrostor up there measuring the humidity. They have a tiny little aneroid barometer in there to measure the pressure. They have a little eco-friendly battery in there that powers the instruments and radios the information back to the ground station. And so on. They're all just out there taking in situ measurements as this balloon flies up into the atmosphere. They also have a GPS. Nowadays, modern radiosondes determine their winds using GPS. They measure their current latitude and longitude, therefore their position now, and then let's say 5 seconds from now they'll measure their latitude and longitude again, and based on their change in position with respect to time, they figure out the speed of the winds that the balloon is being pushed around by. Pretty straightforward. It's just done nowadays with GPS. The GPS does not actually determine the height of the balloon. The height of the balloon is actually pretty slick. It actually, the radiosonde takes the temperature and pressure information that it has been gathering since it left the ground, and from that information it can figure out its current height using an equation that is every atmospheric science major's best friend, the so-called hypsometric equation. Hypsometric is a word that means measuring height. Hypso is height, metric, measuring. We're not, at this point of the class, going to talk about the hypsometric equation. I'm actually a little bit torn as to whether we are going to see it later in the semester. But it's an equation that basically says you can always figure out how high above the ground you are if you know the temperatures and the pressures below you. And since the balloon just passed through all of those temperatures and pressures, it does know them, so it can always figure out its height. And it actually can figure out the height way more accurately than the GPS can. Cheap radiosondes are weirdly expensive. If you go online and want to buy some radiosondes for some scientific project you want to do, they're a couple $100 each, maybe $500, something like that. Strangely expensive. It's partly just because of all the calibration and so on. It's partly just because the world doesn't use that many of them. There's just not that much of an economy of scale to them. So as a consequence, the governments of the world don't want to launch these any more than they have to, despite the fact, of course, that they are part of the routine weather observations that most countries take. If I just show you here, this is a map of where in the United States we launch weather balloons. Every day, twice a day, these locations that you have labeled there are National Weather Service offices, and they launch those balloons twice a day as part of our routine measurements of temperature, pressure, humidity, winds, etc. that go into how we make forecasts and so on. And you can see across the United States, I forget the exact number, it's about 85 or something like that, locations we launch them twice a day. Because why don't we launch more? Well, because we don't really feel like spending that much money. And plenty of countries don't launch them at all. Some only launch them a few places. They're just an expensive way to understand what the weather is doing. It's an expensive way to get in-situ observations of the weather aloft. Alright, we have wrapped up the in-situ part then of this very long lecture. You still have the remote sensing part to go, but let's do a couple quick questions about what we just saw. Question 10. Grandpa just called, and he said that it rained 2.13 inches at his house last night. Apparently Grandpa has a standard rain gauge that he used to take that observation. I have a picture of a standard rain gauge if you don't remember what that one looked like. True or false? Could he have gotten that observation from a standard rain gauge? Alright, make a choice from those two options and get some feedback before you move on to question 11.